Alrighty, so we've been speaking so far about carbohydrates as chains of carbon atoms. And these are chains of carbon atoms that feature an aldehyde or a ketone functional group, and that falls into this general kind of 1 to 2 to 1 ratio of carbon, hydrogen, and oxygen. And of course, I'll keep using glucose as an example. Now, I've also used the term polyhydroxylated to refer to the numerous hydroxyl groups that are in these carbohydrates. And really, I bring all of this verbiage back up to hopefully spark your ability to see that carbohydrates have all the makings of an internal or intramolecular, I guess, reaction between the carbonyl carbon right here and one of the hydroxyl groups. Because essentially what we have is carbonyl and alcohol chemical reactions just kind of waiting to happen. And what happens when an alcohol nucleophile attacks an aldehyde or a ketone? Well, you know, if there's an excess of alcohol, we end up with a product that is either an acetal or a ketal. But what happens if there's only one nucleophilic attack by an alcohol? If we just have one alcohol, and that's going to be the case in the ring-closing intramolecular reaction we have going on here. Well, in that case, we end up with a hemiacetal or hemiketal. And really, that terminology is just kind of a review of acetal and ketal chemical reactions that would fall under, I guess, if you're looking in an organic chemistry book, aldehyde or ketone reactions, probably in the carbonyl section. So let's show how this process is happening in the context of our glucose over here. First, I'm going to highlight the particular hydroxyl oxygen that's going to act as the nucleophile. So we'll make that pink. And after being deprotonated, so after losing this proton, this oxygen is going to have an extra set of electrons right here, and those electrons are going to target that carbonyl carbon. So I'll draw the carbonyl carbon in green, and remember that the carbonyl carbon has a partial positive charge on it. It has a partial positive charge because a lot of the electron density in this double bond is being hogged by this oxygen. So the oxygen has a partially negative charge and the carbonyl carbon is partially positive, and that makes it a perfect target for the nucleophile that's been created in the deprotonation process of this oxygen. And so after the oxygen's electrons attack this carbonyl carbon, what's going to happen is the electrons from this double bond are going to kind of kick back up to the oxygen up here, and eventually they're going to attract another proton and will form another hydroxyl group out of some of the electrons from that bond. Now you might be asking, and it's a perfectly valid question, why it's this particular oxygen, the one that I've highlighted, that's acting as the nucleophile. And you're going to see as soon as I get the product drawn that we've formed a 6-member ring. So it really has a lot to do with product stability. And if you remember, the basis for the formation of the ring in the first place was the increased stability over the straight carbon chain. So it makes sense that we're going to form the most stable ring that we can. Now, when we end up with a 6-membered carbohydrate ring, such as the case with glucose here, we call the product a pyranose. Pyranose, the os again as the suffix for sugar, and the pyr part to indicate that this ring is sugar with 6 carbons. And then if the carbohydrate ring is a 5-carbon ring, we call it a furanose, which is a bit easier for me to remember because furanose and 5 both start with the letter F. So that's kind of the memory jogger for me. And maybe a good example for that would be ribose with its 5-carbon chain, but I'll kind of stop there because almost every ring forming carbohydrate that I can think of with biological implications at least forms either a 5 or a 6-membered ring, so pyranoses and furanoses. So just by convention, you can see that I've placed the O in this corner up here, and that places the formerly carbonyl carbon down here right below it, and it's actually no longer the carbonyl carbon, but it's still significant because it's the only carbon here that is bonded to 2 oxygen atoms, the highlighted oxygen, and it's bonded to another hydroxyl group as well. So I'll keep it distinguished in color, and we also distinguish its name now as the anomeric carbon. So that's the anomeric carbon. And then we can go ahead and fill in the rest of the substituents in the diagram. So a hydroxyl group, and another, and another. And we call this diagram a Haworth diagram. So Haworth diagram. And the Haworth diagram doesn't show us the actual configuration of the ring, because in reality, six-membered rings are going to show up in a more stable chair shape, but it is beneficial in telling us which substituents are above or below the ring. So to keep this convention straight in my mind, I remember the phrase downright uplifting. So downright uplifting, kind of a play on I guess the phrase that's downright uplifting, but downright uplifting, because as I fill in the substituents, those on the right side of the Fisher diagram will point down, and those on the left side of the Fisher diagram are going to point up. So we can actually see that. That one's up, and we'll make sure that this number's off right. This one's up as well, and maybe we'll name this, or maybe we'll start numbering with 1, 2, 3, 4, 5, 6, and we can do that over here. This would be 1, 2, 3, 4, 5, 6. So our 3 carbon in the Haworth diagram is pointed up, and our 3 carbon on the Fisher diagram has its substituent on the left, so downright up left. And as we get to the last carbon group, which kind of forms this tail down here, I remember that if it's a D sugar, that group is going to point up in the Haworth, projection. So this is a D sugar, and you can see in the Haworth projection that this last carbon points up as well. And really this is going to be the case for a lot of sugar chemistry that you deal with, because again, we're enzymatically programmed to digest D sugars, so we often end up with this last group pointing up. Now the last thing I want to show you is the chair conformation. So the chair conformation, and that's because this is the kind of diagram that's going to give us a sense for the actual configuration of D-glucose, but it really does just follow suit with the Haworth projection as far as the substituents being above or below the ring. So let me just kind of keep filling in the substituents here, and I'll number them off again just so you can kind of see that there's some consistency here. So we've got 1, 2, 3, 4, 5, 6, and again this 3 carbon right here is the only one with the hydroxyl group pointing up. And I guess I better change the color of our 1 carbon to keep that consistent as well. Now I didn't indicate the position of the anomeric carbon's hydroxyl group yet, because I think it makes more sense to show it in this diagram. Remember, that the original nucleophilic attack by the oxygen, way back over here, that could have created 2 different products, one with an R configuration about the anomeric carbon and the other with the S configuration. So that last hydroxyl group can actually be in 2 different positions. On one hand, the hydroxyl group would be cis to the last carbon in the equatorial position. So it'd be cis to this last carbon over here, and it's in the equatorial position, and we call this the beta anomer. Then on the other hand, I guess, it could be trans to that last carbon group, which would place it in the axial position down here. So I guess it could be down here in the axial position, and we call it the alpha anomer when the hydroxyl group is in the axial. And I kind of remember that a little bit easier. Alpha for the axial position of that substituent. And I guess I've also heard that fishies are down in the sea and birds are up in the air. So if that helps you keep them straight, you might be able to use that also. Now you've got to remember that what caused this ring to close in the first place was some amount of acid or base. And the amount of acid and base in water is actually kind of capable of doing that, because that's what facilitated this ring closing process in the first place. And in water, the ring can actually open and close spontaneously. And when it opens up, the C1 and C2 bond right here can actually rotate, and when it closes again, you can form either the alpha or the beta product. So this thing is constantly opening and closing to form the two different products. And we call that process where it opens and rotates and closes again mutarotation. So this thing is mutarotating in the water at all times. So mutarotation, and the outcome is that we end up with both configurations, the beta and the alpha, in the equilibrium concentration. So for glucose, that's going to be about 36% alpha and about 64% beta. And the reason that the alpha configuration is less favored in equilibrium for glucose is because the transpositioning of the hydroxyl group creates some steric hindrance, but this is pretty individualized for different sugars. So I guess the most general rule, I suppose, that you could apply to all cyclic sugars would be to say that the beta anomer, that the beta anomer is the one with the anomeric oxygen in the cis position with respect to the last carbon.